The topic for this lecture, for today's lecture, is going to be a discussion of the class PSPACE. So this is, the class of languages accepted by Turing machines that use polynomial space. And given the previous lecture, we know that NP is contained in PSPACE, and we know by Savage's theorem that PSPACE is the same as NP space. Now, given these complexity classes, a natural question that you might have is, okay, but does this really capture problems of interest? NP, as we discussed through the discussion on SAT and all of these NP completeness reductions, we saw that there's a large class of interesting problems that that lie in NP and are NP complete. And so that it's almost like a backward justification for why you would want to study NP. And the same question can be asked of basically every complexity class that we define, that what are the problems that it's capturing, or is this just some sort of esoteric notion? And today I'd like to tell you about problems that are very natural, that are really PSPACE, that are in PSPACE, and that they capture PSPACE. These will be PSPACE-complete problems. So first, let us define what it means to be PSPACE-complete. So let's define PSPACE-completeness. So we'll say L is PSPACE-complete if the following two conditions hold. So L is in PSPACE. That's sort of the usual part. And the second is that for all L prime in PSPACE, for all L prime in PSPACE, L prime reduces to L, right? And if only two holds, then we say L is PSPACE hard. And just analogous to NP completeness, co-NP completeness, PSPACE-completeness, PSPACE-complete problems one can think of it as are the hardest problems in PSPACE. So this is the definition of PSPACE-completeness, analogous to the definition of NP completeness. Indeed, this definition of completeness holds really for any complexity class that contains P. That this notion makes sense, right? For any complexity class that contains P, we can define the notion of completeness with respect to that class. Now recall that one of the important theorems that we proved was sort of the Cook-Levin theorem. So Cook-Levin theorem says that SAT is NP complete. Therefore, in some sense, satisfiability has this important role within NP. Indeed, any NP complete problem has this role. So canonically, we can think of the entire class of NP are essentially languages, that can be converted to SAT. And so similarly, we had the problem tautology, which was co-NP complete. And so what I'm going to show you is an analogous language, which is PSPACE-complete. So let me define something called quantified Boolean formula, also called Qbf. Okay. So what is quantified Boolean formula? So I'm going to describe what an instance is. So the instance is the form. So you can think of SAT is asking, does there exist a satisfying assignment? And tautology asks, is it true for all assignments? Quantified Boolean formula has a mixture of there exists and for all. So we'll say that the way we'll write this, we'll say Q1 x1, Q2 x2, Q3 x3, up to Qn xn. So I'm describing what an instance looks like of phi of x1 to xn. So this is a formula. This is some formula, like a 3CNF or whatever have you. Each Qi is either there exists or for all. So quantifiers can switch. So for example, you can have a statement like there exists x1, x2 such that for all x3 and x4 there exists an x5, such that maybe x1 or x3 and the negation of x5 or x4 or x2 negation, something like that. You can have some kind of formula here. This seems like a much more complicated problem because now it's not clear that there is a certificate when this is true. So the question is this true? Is this true? So instead of saying satisfiable, because it's not really satisfiable in the sense of you provide a satisfying assignment, we would just ask, is this true? So the language Qbf is the set of all true, Qbf formulas, or QB formulas, quantified Boolean formulas. So I'll just write that down. So the language Qbf is really the encoding of all such Qn xn phi of x1 to xn, all of these where this is true. It's the encoding of all of such statements that are true. Okay, does this make sense? What Qbf is? Note that Qbf, sort of contains SAT, because if you replace all the Qis, if all Qis are there exists, then this is just SAT. If all the Qis are for all, then this is tautology, right, which is essentially the complement language. But you can mix and match in any way in Qbf. Any questions about that? Okay. And so our main theorem, the main theorem for today, is that Qbf is PSPACE complete. So this is very interesting now, because just as SAT was NP complete, Qbf is PSPACE complete. And so now PSPACE, in some sense, is represented canonically by quantified Boolean formula, which is really nice that we can actually sort of capture the notion of polynomial space, the notion of polynomial space algorithms through this sort of logical formulation. And the proof, once you have all the details, is not that hard. It actually, it's not that hard given that we saw the proof of Savage's theorem. And it's going to sort of follow some of the ideas from Savage's theorem. The notion of the configuration graph and the reach that we define are sort of key ingredients. And those were sort of the main insights you need. Once you have those insights, the proof of this theorem will follow. So first, let's prove the first part. First, let us prove that Qbf is in PSPACE. And you might think that it shouldn't be that hard, because technically a PSPACE machine in polynomial space can evaluate all possible settings. It can evaluate all possible settings. It can't store all of them, but it can afford to sort of loop over all of them and then try to determine whether this is true. And one can do it sort of recursively as follows. So I'm going to write down a PSPACE algorithm. So I'll just call it decide. So this is decide Qbf. This just decides whether a Qbf instance is true or not. And so Q1 x1, Q2 x2, up to Qn xn of phi x1 to xn. Okay, so I'll say that first step is if n is 0, well then just output true. That's just the trivial base case. So if you have no quantifiers, then this is just trivially true. Now what we'll do is we'll set x1 is equal to 1 and call, I'm just going to call it decide, not put decide Qbf because it's a little long here. So decide, okay, so Qbf, maybe I'll put it in here. And then you have Q2 x2 up to Qn xn of phi of 1 x2 to xn. The other will set that we'll set x1 to 0, and we'll call the decider on essentially the same quantification, but in the formula we simply set x2 to 0, x1 to 0. And so if Q1 is the existential symbol, then we say if either of the calls return true, then you return true. And if this was the universal quantifier, then we'll say if both of the calls return true, then return true, and otherwise we just return false. Okay, so does the algorithm make sense? It's sort of a fairly straightforward recursive procedure, right? All you do is you say, well, okay, so you take the first variable and you say it's either going to be true or false, so set it to be both true and false and just see what happens. Excuse me. And the only if this was an existential, if any one of them are true, then you say it's true. If it was a for all, then both of these calls would have to be true to return true, and otherwise you return false. Any questions about this procedure? Any questions? Okay. So now we need to see how much space this requires. So we used, and I'm somewhat abusive notation now. I'm using n as the number of variables. I should really use it for the size of the instance. but I'm just going to stick with n. So n was the number of variables. Let m be the size, just the size of the formula encoding. Right, this is basically whatever, if it's a CNF or DNF or whatever have you, it's the total size to write this down, right, in ASCII. And so let's just write a recurrence. This is the space where you have n variables and a formula of size m. So well, okay, so let me first start with, suppose you have this being 0 and m, this is just O of m. Meaning that if you have no quantification, then you just have the formula with variables. The variables have been set to either 0 or 1. So it's just going to be the same, it's going to be O of m. Whatever you use to encode the original formula is going to be an upper bound, because all you did was you set values to each of those variables. Okay, is that clear? Now, what is the space required for this? Now, note that over here we can reuse the space. So we can reuse the space from the second step. So the way that this algorithm would work here is, before calling this, it would have to actually just write down its own input, just so that it doesn't forget what it is after this call ends. So it simply writes down the formula over here, then goes ahead and uses extra space to call this, uses the same space to make the second call, because all it needs to do after the call is to store the answer, which is just 1 bit. And so it only needs the space required for n-1 variables once. It only needs it once because it can reuse the space. Plus whatever it takes to encode everything, which is maybe m plus n. And I say m plus n because you have maybe m is the size of this encoding, n is whatever you want to encode, encode the variables. And again, I'm being loose about these things. You may need like an extra log. Let's just, okay, so just to be formal, I'll say m plus n log n, because each of these would maybe be log n bits to represent the index. But if you uncoil this recurrence, what it basically says is every recursive call is going to take that much additional space, and they're at most, the depth of the recursion tree is at most n. And so what you get is that the space nm is O of it would be O of nm plus n square log n, and this is just polynomial in the size of the instance. Right, this is just polynomial in the size of the instance. So this gives a polynomial space algorithm. Is this clear? Any questions about this? Okay. Good. Let me just. All right. So that gives the polynomial space algorithm, and you can see, this sort of theme of reusing the space appears over and over again. We did this for Savage's theorem, where we did multiple recursive calls, but we can reuse the space and just store the answer. So all we need to do in the recursion stack is you need to store the argument. Once you store the argument, then you can basically reuse the space for all the recursive calls. Okay? So this is proving the first part, that Qbf is in PSPACE. Now we need to prove that any PSPACE language can be reduced to Qbf. So now let's say some L is in PSPACE. Let M be a P of n space Tm that decides L, and this is some polynomial. That's why I call it P of n. Right? So there's some polynomial space machine that decides this language. Now remember what we said. Okay, so now we need to come up with a reduction. So let's sort of be careful about this. I just want to write it out so that it's clear. So given x, we need to construct a Qbf instance called C of x. We need to construct this in polytime such that x is in the language if and only if C of x is true. Right? This is what we need to do, and we need to do this in polynomial time. So we need to give an algorithm, a polynomial time algorithm, that given an x constructs a Qbf instance such that that Qbf instance is true if and only if x was in the language. This is the reduction showing p-space hardness. Okay. So what is C of x going to be? This is going to be the same reach predicate. The reach predicate that we defined. So recall that C of x is going to be some encoding. I have to write this as a Qbf instance. It's going to be, I'll say, equivalent to, because I haven't told you how to construct it, C start, C accept, and there's going to be a parameter here which is P of n. Recall that reach C prime I is true if and only if, or if there's a definition that configuration C prime can be reached from the configuration C in less than 2 to the I steps, or steps or time. Right? This is what the reach, this was a predicate, and we simply just defined a predicate, and we defined a method that computes this predicate. But now what we're going to show is that this predicate can actually be represented by a quantified Boolean formula instance. Okay, so is that clear? So note that C start depends on x, but C accept does not depend on x. C start and C accept can be, computed or written down in polynomial in x time. And indeed, that polynomial is just going to be P of x, where P was the original space bound of the machine. Right? So we said that there is a machine, and now we have to give the reduction. So with the machine, we know that there is some space bound. Given that space bound, we can essentially write down what the starting configuration is. This is simply writing down x, maybe putting blanks, pn, blanks in the remaining spaces, and then putting the head in the right position in the string. And the accepting state again is something that we can write down. So this can be computed in polynomial in x time. The point is now to write this predicate in terms of a quantified Boolean formula. And I'm going to write down essentially recursively. So I'm going to write down a quantified Boolean formula for reach, C, C prime, and I. Okay, where you can think of C and C prime themselves are going to be represented as variables. Okay, remember that, C and C prime are strings, which can be, represented as a list of Booleans, right? Because these are just going to be strings. Okay. Now, if you remember our discussion in Savage's theorem, we said that reach C, C prime I is the same as there exists some C double prime, some other configuration, which is the midpoint, such that reach C, C double prime I minus 1 and reach C double prime C of I minus 1. Okay, this is what we said. So this is going to be sort of an inductive step. Now, just to give you the base case, how do we write this as a Boolean formula? Right, so this just means is or does C prime follow from C in one step? Right, in one step. So think of the way to think of this is, let's just say that C1 was represented as x1, x2 up to xpn, and C prime was written as y1, y2 up to ypn. Okay, where the xi's, yi's, these are Boolean. So I'm just saying this is your input. Can you write down a formula? Can you write down a Boolean formula which encodes the fact that C prime follows from C? So the question is, have you seen this anywhere? Have you seen, well, the thing is we have, so where? Have you seen something like this? This requires a bit of thinking back to, so recall the Cook-Levin theorem and recall the tableau method. Now what the Cook-Levin theorem does is effectively give you a Boolean formula that says, does this follow from this? Does C prime follow from C?
Well, I guess you could say, like, look at the differences between the two, right, and see if they logically follow from one another. Because with like Cook-Levin theorem, with two different states of a Turing machine, that there are only a few different ways to get directly from one state to another state, right?
Exactly. So but you have to encode this as a Boolean formula.
Right.
You have to encode this as a Boolean formula. So you'll say that if x1 was the head and x2 was this symbol, then y1 is going to be this symbol. So in this case, the machine is even deterministic. But the point is that essentially you can write down like a truth table for every yi with respect to the xi's.
Right.
Right? I mean, for every yi, you can basically write down like a truth table of this is all the possibilities of what it is. And that truth table only requires to look up like a few of these symbols.
Sure, that makes sense.
Right? So each yi is just some function. Like each yi is a function of, maybe xi minus 1, xi, and xi plus 1. So what we can do is so note that, okay, so let's walk through this a little carefully to make sure that, all of you follow the construction. So what I can do is, and this is some fixed function, right? We know exactly what this is based on the behavior of m. It's a fixed function based on m. So we can write down a formula which I'll call phi of x1, x2 to x p of n, y1, y2 to y p of n, that is true if and only if C prime follows from C in a single step. Right, where again C, this is C prime, and this is C. Right, you just write down a formula that says, is y1 going to be the appropriate function of I minus 1, xi, and xi plus 1. This is a truth table, so you just encode that truth table as a circuit. And you just sort of put down that circuit, and all of these have to hold. And this is again what we did in the Cook-Levin construction. So is this clear at this point? Questions? Okay. All right. So now, okay, let's go back to this picture. So we know that reach, this is essentially, equivalent to this formula on C and C prime. Some phi, where again C and C prime are like, encoded as these binary strings. And reiterating reach C, C prime I, more general version, this we said is there exists and reach C double prime C I minus 1, right? We just sort of said this. And again, now I could imagine this is again essentially it's just going to be some list, Boolean list, or this is some string, so I can just think of this as z1 going all the way up to z of p of n, right? Those are, I'm just encoding this as a Boolean string. Now it seems like this gives me a recurrence, right? So I can write a formula for C, C prime, and I if I had a formula for C, C prime, I minus 1. And why can't I just use recursion to do it? Because I know in the base case I have a formula. In the base case I have a formula, which is when this is 0, I have just a formula, and I know that this true reach C, C prime 0 is true if and only if phi of C, C prime is true. So why can't I just use induction over here and get the final quantified Boolean formula instance that I need? So does my question make sense? My question makes sense. So the thing is, you could keep doing this by recursion, and you would end up with a formula. You would end up with a Boolean formula with quantifiers, because you have this there exists. And so you would end up with these quantifiers, and then you would end up with a quantified Boolean formula instance. There's a catch here. There's something wrong here. I mean, my argument is correct. Why doesn't this give the reduction? Why doesn't this give a reduction?
The resulting formula is too long.
The resulting formula is too long. It'll be exponentially long.
Yeah, because there's exponentially many possible states of the.
Oh, I see.
Well, because I guess technically the way to think of it is, what do we want? We want to look at this. C start, C except, P of n. This is the one that we really want to encode. And so if you apply this, the recursion depth is going to be P of n. And the formula size will be 2 to the P of n. So by simply applying induction or recursion, we get a Qbf instance of size 2 to the P of n, which is too large. Okay, does this make sense? Because it's 2 to the P of n, because you're going to encode something here, you're going to encode something here, so there's 2 instances of the I-1 that you need to encode, and that's going to lead to sort of 4 instances of the I-2, 8 instances of I-3, so on and so forth, so eventually you get 2 to the P of n instances. You might even observe that the Qbf instance that you generate through this only has existentials. It's actually going back to SAT. You're not even using for alls.
The existentials are just there exists C double prime, right?
Right, but then this is now going to have like there exists a C triple prime, and this is going to have there exists some other. Right. So, I mean, it's literally saying, does there exist a path? So you just write out the entire path, and then you say, okay, then you can just check each individual step using the basic Boolean formula. Right? This would be saying, does there exist the entire path? And remember, by the ideas in Savage's theorem, there was this notion of reusing the space. And here it seems like we're not reusing the space. We're just duplicating this formula. And so we're going to use we're going to use a trick to see if we can reuse the same formula. This is really clever. The ideas are, again, very similar to what Savage has in his proof. So I'll say reach C prime of I. Okay, so you have to watch what I'm doing here. So I'll say there exists C double prime. So again, all these are configurations. C prime, C double prime, these are all configurations. Right? This is a configuration. And so each configuration can be written as some Boolean string of length P of n, right? Each configuration is like a Boolean string, so each of those are variables. So it's like I'm saying, do there exist a setting of these variables which represent configuration C double prime? Now such that for all configurations D1 and for all D2, so I'm going to add these sort of dummy variables so that I can compress this and encode it into one formula, and we'll see. I'm going to write something down over here. So I'm going to use like if notation here. But you'll see that, you can always encode that back as and or. So essentially it's saying if D1 is equal to C and D2 is equal to C double prime, or D1 is equal to C double prime, or D2 is equal to C prime. Remember, this is where it starts, this is where it ends. Okay. I'm going to put these themselves in a bigger parenthesis. So I'm going to say if this holds or this holds, then reach of D1, D2, I-1. What is this saying? So this is C prime. And now you say, here's my C double prime. Now I want to say that reach C double prime, I-1, reach of C double prime, C prime, I-1. But I want to combine them both into just one representation. So I'll say, okay, now choose a D1 or D2. If D1 or D2 don't correspond to these, then I don't care. But if D1 was C and D2 was C double prime, then the reach should hold. And if D1 was C prime and D2 was, I'm sorry, if D1 was C and D2 was C double prime, reach condition should hold with I minus 1. And if D1 is C prime and D2, if D1 is C double prime, D2 is C prime, then this reach condition should hold. And that's what this encodes. So this is giving me an alternate recursive representation where I only have to use a reach of I minus 1 once. And everything else I can, basically encode. Does this make sense? So please ask me questions if this is not clear. And this is the heart of the construction.
You said that the D's are just dummy variables?
They're dummy variable. Okay, so in some sense, what you want is you want to check both of these.
Right.
You don't really care about checking reach between any other pair.
Right.
So this is like looping over all pairs D1 and D2. That's the for all. And this is saying if D1 and D2 are not these endpoints, then just ignore it.
Okay.
But if it is C and C double prime, then you want to check reach. And if it's C prime, C double prime and C prime, then you want to check reach. That's what this and this are doing.
Well, I guess I'm a bit confused about choosing C double prime, because in the original algorithm, right, it sort of goes through every possibility. I can see like why you would not want to choose any endpoint other than C or C prime, but like how would you know if C double prime is the actual midpoint before you like actually test it, right?
So the thing is, think of it this way, that you're going to run. Okay, so let's go back to which one? So let me pull out my notes from previous lecture. Yeah, let me pull out the notes from Savage, and I think maybe that will be clear. Okay, so this is just the notes from Savage's theorem. You remember that you wanted to go, the reach was from U to V, and you chose a W.
Right.
So now let's just say that you didn't want to have two lines of code. So here you're making two recursive calls. You're reusing the space. I want to write a piece of code where there's only one line where you actually make a recursive call.
Okay.
So what I'm going to do is I'm going to actually, instead of having W, I'm going to now have a triple for loop. I'm going to loop over W. Then I'm going to loop over two more variables that I call x and x prime. And I'll say if x was U and x prime was W, then call reach. So if this condition holds, or if x prime was W and x double prime was V, then call reach, right? So that I could just pack that. I could pack this into one single line. Let me write this out here.
I think that makes sense.
So I just want to have a single line of code, because then when I unpack the code is not going to blow up too much. So it's almost like I'm going to basically write this, instead of thinking of it as a recursive algorithm, I have to write out a formula, which is like taking the code and just unpacking it completely. So what I could do is I could say, for all W, and then I'll say for all x prime, if if x is equal to U and x prime is equal to W, or x is equal to W and x prime is equal to V, then call reach x prime I minus 1 and store the answer. Like, I could replace this code by this piece of code here.
So that's instead, so it's not like you're making two recursive calls in the same loop. It's like you make one recursive call, and then you go down that stack, and then later on you might make the other recursive call, but it won't be bundled together.
So yes, exactly. I mean, I guess the complication is here you're trying to think of the space of the algorithm, and
Right.
here you're trying to come up with a Boolean formula.
Okay.
So a Boolean formula is not an algorithm, right? It's almost like in an algorithm you can loop. In a Boolean formula you can't loop. You have to sort of write everything out explicitly.
Right.
So this is sort of like a clever way of writing it out explicitly so it doesn't blow up too much.
Okay.
Because now I'm
Right.
gonna replace this with its own triple for loop. Right? I'm gonna sort of
Right.
like expand it out. Then I'm gonna get reach of I minus 2, which I'm gonna replace by its own triple for loop.
So your main constraints is that you have to write this as a Boolean formula, and with the Boolean formula, I mean, you can't just write it. It's going to blow up.
Exactly.
Because you don't have the same tools as you would just a regular algorithm.
Yes.
So then you have to do this trick.
Yes.
I see.
Because you want the size to be small. Right? In the end, you want the size to be polynomial in n. Whereas if you just do it, like if you basically took this piece of code and you literally unpacked it. So you said, instead of saying compute this, you now write out the code for that. And then you write out the code for that. And you kept doing this. You'll see that this is blowing up really quickly. The length of the code is going to blow up.
I see.
But here, the length of the code is not going to blow up as much. This is more time efficient. This is time inefficient. So what the time means is you're introducing more and more variables here. You keep introducing more variables, but the benefit that you get is that the final code that you write is actually not as large.
I see. So this is analogous to just writing out all the recursion in an algorithm, and as if it were one block of code.
Exactly. It's like you're like unpacking all the recursion and writing everything explicitly. And the reason you cannot really you cannot use recursion in your Boolean formula because you have to write out the Boolean formula explicitly. What you can do is you can say looping as a for all. Right? You can say for all or looping is often a for all or there exists. Like find something that has this property or check that this property doesn't hold for everything.
Right. And that's why you don't want to have two different recursive calls, because that's not going to be efficient at all.
That's not going to be efficient when you unpack the code. Like the code length is going to blow up. The algorithm in some sense is the same. Or so this is maybe the challenge, right? So far you're trained to think about running time of algorithms.
Yeah.
But now you have these other things. You have the space complexity of the algorithm. Here, it's almost like you have the representation size of the algorithm. Like how many lines of code is it? Which is like a completely different notion. Because the number of lines of code is kind of analogous to the size of the Boolean formula that we're going to come up with.
Yeah, I think having to think about this, not as much as the time complexity, but as other things like the space, definitely makes this a little bit more challenging.
Yeah, it takes some getting used to because you need to now think of different computational resources here.
Right.
And so now you can reach CC prime I as this formula. And then you need to use recursion or induction to find out what this is. But then you'll see the size is going to blow up more benignly because you only use one instance of the I-1 formula. This is a bit, you have to do a double take on this and like go and look at it. But so any questions? I mean, is this making sense? It's a bit of a challenging. It's not the most trivial thing to look at, or to even understand why you want to do something like this. And so now I'll just write the recurrence here. So the size of the formula or the Qbf instance for parameter I. So I'll just refer to this as the size of I. Right, this is just saying what is the size of the Qbf formula you're going to get from here. So the size of I is going to be at most, I have to write this out, that's going to be size I-1 plus whatever it takes to write all of this. Right, this has to be encoded, but this is just going to be something which is linear in P of n. This is like O of P of n. And because you have to write out all of these variables, you have to say if z1 is equal to the corresponding variable in d1, and you have all these things you need to write. And as we argued, the size of 0, this is also at most, this is O of P of n, and this is going back to the Cook-Levin type construction, that there's going to be some formula that you write, but that formula is just going to be linear in the size of the configuration. Right, this is just because for every, as we said, for every yi, you just have to check is it some specific function of xi minus 1, xi, and xi plus 1. This can be written out as some kind of Boolean, a small Boolean circuit, like a small formula. And so if you work out the recurrence, and this is again, you see the square, this is the same square that came up in Savage's theorem, that this is O of P of n squared. Okay, so the size of Pn is O of P of n squared. So this means that reach C start except Pn has a Qbf of size O of P of n squared. Right? This is sort of the main punchline that we end up with. That you can write a quantified Boolean formula that has of size O of P of n squared, and indeed this Qbf can be constructed in polynomial time. Like this can be constructed in polynomial time given x. Right? So I'll sort of write that out separately. So reach C start C except P of n has a Qbf of size O of P of n squared, and given x, C start and C except can be written in polynomial time. And so this entire formula here can be written down in polynomial in that much time, or in polynomial in that much in P of n. Right? Because one could imagine that what you simply do is just write out C prime with P of n, and then you just like plug in the values of C start and C end. Right? And so therefore this Qbf can be constructed in poly P of n time. And of course, as we said earlier, X is an L if and only if reach C start C except P of n is true. So this completes the proof of the p-space completeness of QBF. This proof is, it's something that you need to go back and look at again to understand what's going on, but QBF is p-space complete. Any questions about that?
So wasn't it that every quantifier just ended up being existential, and doesn't that just mean that it's sat really?
Oh no, we used universal quantifiers here.
Oh right.
So that's the key, right? We used universal quantifiers to cut down the size representation.
Right. Okay.
Yeah. Any other questions?
So just to reiterate,
yes,
we've shown that any formula or any problem in T-space can be reduced to a formula, a QBF formula that is also in T-space, and that shows that QBF is P-space complete.
Exactly. So, or technically, given for any language, so fix any language in p-space, given any x, string x, to determine if x is in the language, you can basically construct a QBF, which is of polynomial size. And that QBF is true if and only if x was in the language.
I see. Gotcha.
So it's like you're encoding whether this string is in the language using a QBF.
Just like with the other, with other kind of reductions that we talked about before with P and NP.
Yes, and actually this is like, you can think of it as analogous to the Cook-Levin theorem, right? We actually use the Cook-Levin, we use the construction of the Cook-Levin theorem just for the base case here. But Cook-Levin says the running of an NP machine can be encoded as a Boolean formula, but with existentials. The running of an NP machine is really can be done through this satisfiability instance. The running of a p-space machine, you can do it through a QBF.
I see. So it's really a lot of the same arguments.
It's sort of, I would say that the seed idea comes from Cook-Levin, but really the use of reach, it comes from Savage's theorem.
Sure.
So you're sort of combining both of these ideas. You're taking this notion from Cook-Levin that in effect the running of a Turing machine can all be encoded through just some kind of Boolean formula.
Sure.
Right? So that's one piece. And then you kind of take ideas from Savage's theorem that it's all about reachability in the configuration graph. And the way to sort of get compressed representations of the reachability is to look for the midpoint and then do two recursive calls. And here it says that two recursive calls can kind of be, from a formula perspective, can be combined into just, making, sort of putting one instance of this formula for I minus 1.
That makes sense.
So let's go back to this, SAT is NP complete. QBF is p-space complete. Now you see there's, and you've also heard a lot of this is like P versus NP, is really asking, does SAT have polynomial time algorithms. But we can also ask, what about P and P space? Which is, does Qbf have poly time algorithms? And indeed, you could think that, to me, sometimes when I step back and look at P versus NP, I'd say, well, actually, what about P versus P space? Which, again, is a big open question. Is P equal to P space? We don't think so. We think that, it could be possible that, P is equal to NP. So for SAT, you have a polynomial time algorithm, but that does not mean that you would have an algorithm for QBF. And so it seems like an even easier problem to look at P versus P space. But even that is something that we don't know. It is, is entirely consistent with our knowledge that P is equal to P space, which should also show that P is equal to NP, because SAT is a special case of QBF. And so the P versus P space problem is like an equally challenging and or I would say not equally. It's a big open problem, and we don't have any insight into that, although we don't think it's true. This dichotomy is actually useful to think about, and Aurora Barak talk about this, and I like this. I like this viewpoint. So it's like NP. That's like what they call puzzles, and P space. These are like games. Let me give you sort of a high-level intuition of what this means, and this will relate to like these recursion tree or the recursion ideas we were talking about. So consider Sudoku. And sort of the n cross n version. So this is actually known to be NP complete. So this is NP complete. So if you think about Sudoku, but I'm assuming that all of you know what Sudoku is. Is that a valid assumption? I can take a different example. We can take a different example instead of Sudoku.
I think that's fair.
It's fair? Okay.
Sudoku's fine.
Okay, so what is Sudoku? It's like you have these numbers written here, and then you have to fill in. You have to fill in according to certain rules, right? So suppose you did a brute force, just build a recursion tree. So what are you going to do? You're going to start at the root of the recursion tree, and then you have a bunch of choices. You can say, what am I going to put there? So I'm going to put one of 1 to n. So I have these n choices here, maybe. And then from here, I have some other choices. I'm going to put those choices down here, and then I have some other choices. I'm going to put those choices down there, and I go all the way down. And so I have some tree here. I mean, this tree is like exponentially large, right? In this case, it would even be, it would be like super exponential. It would, whatever. It's like 2 to the n log n. It's 2 to the poly n, right? So this, you have 2 to the poly n leaves. Now, what is the NP question? Is basically find a leaf that wins. Right? Where winning is if you were to satisfy all the constraints of Sudoku. So that would be, it's about finding a leaf. That's what puzzles are like, right? If you actually have any puzzle, it's like you're trying to find a solution. So if you've played a lot of these puzzles where, analogous to Sudoku, you think about how you play it, you have a recursion tree, right? You make a choice, then you've got a bunch of other choices that open up, and then you have to take one choice from there, and you have to take these choices all the way and end up at a solution. And you're trying to find a clever way of making the choices so that you actually end up at something that wins. Now think of a different version of Sudoku where you're playing against an adversary. So Sudoku is not the perfect example for this, but just bear with me. Let's just sort of take this forward to see what's going on. Suppose you're playing Sudoku. So make Sudoku into a game. So what is the game? So it's going to be me versus an adversary. So my aim is to solve. The adversaries is trying to prevent a solution. So here's what's going to happen. So I play, meaning I put a number in a square. Put a number somewhere. Now the adversary plays. Again, so the adversary has to follow the rules, right? Adversary plays without breaking the Sudoku rules. If I cannot play, that means I cannot put a number without breaking the rules, or the adversary cannot play. I lose. If we end up at a solution, if we end up at a full solution, then I win. Does the game make sense? Does the game make sense? I'm converting Sudoku into a game. And the game is, I put a number down, the adversary puts a number down. I put a number down, the adversary puts a number down. We always have to follow the rules of Sudoku, right? Which says that in any row, in any column, in any box, you should only have one number of each, from 1 to n. But the adversary is trying to thwart a solution, and I'm trying to get to a solution. So it's like chess almost, right? So chess also has the same thing, right? I have a particular solution that I want to get to. That solution is checkmate of the other person. The reason I wanted to use Sudoku is really so that I start with an NP-complete problem. I want you to think about thwarting a solution. Now, if you think about it, and so you can think of Sudoku always, starts with some original configuration that's, in this case may or may not be as important. But the NP-complete version, NP-completeness is, there exists setting of numbers that leads to a solution. But the PSPACE version is there exists my move so that for all adversary moves there exists my next move such that for all adversary moves etc., etc., we get to solution. We end up at solution. Another way to think of the recursion tree is, let's go back to the recursion tree. In the NP version, you just have to find a path that goes down. But in the PSPACE version, it seems like you have to actually look at the entire tree. It's not enough to find one path, because if this path exists, once you go here, the adversary might move you somewhere else where no path exists from there. So before you make a move, you actually have to check about all the adversary's possible moves, so on and so forth. And so this is like games played against an adversary are like PSPACE. So if you take a puzzle, you can convert it to a PSPACE version. And indeed, that puzzle for us is SAT. SAT is like a puzzle where you have to just find a satisfying assignment. You can convert that to a PSPACE version through alternation of quantification. And the existence of the adversary is like the for all, and I'm a there exists. So there are actually games of what are called the existential and the universal, like players who are playing a game. And the existential player is saying, like, can I find something so that no matter what the adversary does, I have a response? And those problems or the languages or the games are PSPACE-complete. So often versions of chess, versions of games where you have to make a move so that no matter what the adversary does, you have to have a response, often lead to PSPACE-completeness. And that's where PSPACE becomes very natural in applications where you're thinking of, interacting with an adversary. Any questions about this? Does this discussion make sense? This is high level, but I wanted to give you some intuition about NP versus PSPACE.
I have a question.
Yeah.
Well, I can see how this adversarial game corresponds to Qbf, with the universal quantifier, and I can see how a regular puzzle corresponds to like SAT, and how it also corresponds to NP. But I guess I don't totally see the connection between NP space to like a game, like just like the space notion of it. How does that correspond? I'm not sure if there even is a direct correspondence.
There is actually. We can see this, right? So if you think about NP, it's all about just finding a path down the tree.
Right.
But in the game, it's not enough to find a path. It seems like when you make a move, you have to recursively consider what the adversary can do. So you have to explore, in some sense, all possible paths. Except you don't have to store all the paths. It's enough to just store the recursion depth. But you'll have to explore all the paths in some consistent way.
Okay.
So that's where the PSPACE comes in, because the space is how long it takes for you to store a path.
I see. Okay. Fair enough.
Right, so it's more, so you can say this is exponential time, but it's actually better than exponential time because it's polynomial space. You don't have to store the entire recursion tree. And this is again going back to ideas like Savage.
I see. So that's what's consistent between any game.
Yeah, exactly. The thing is, you don't have to sort of, if you imagine in chess, you don't have to write out the entire trajectory of all possible moves. What you really need to understand is if you make a move, do you have a response for all possible moves that the adversary can make? And if you sort of set that up recursively, you'll see that it naturally it's going down you'll have to store a recursion stack. But you don't have to store all possible moves if you know, let's say that you know that a move is good. That's all. Okay, you're saying this move is good. Now let me look at the next move.
Right.
I don't need to store
minimax, right?
So I'm sorry.
It's just a minimax.
Yes. It's like a mini. Yeah, exactly. It's a minimax. Yeah. So it's this alternation of quantification which captures PSPACE, which is really neat. Like that suddenly that you have this almost this consistent view of NP and PSPACE, which seem, from a Turing machine standpoint, seem like completely different beasts. But this language of Boolean formulas now gives like this sort of unified picture of NP and PSPACE.
That is quite cool. I agree.
Any other questions? Okay. So I don't. The way I like to think about it is every day I want to prove like an interesting theorem to you, but I don't want to do two. Like that would be too much. So I have about 15 minutes left. I'm going to start off on a new concept, and I might revisit the next lecture. So have a look at this is sort of a primer for what we're going to see in the next lecture. So this is going to end our discussion on PSPACE. There's a lot of rich things we can look while understanding PSPACE, but now that you know NP and SAT, PSPACE and QBF, that gives you your basic foundation for understanding space complexity. Now let's look at the class NL and try to understand what NL really means. Because NL, if you think of non-deterministic log space, it seems to have no meaning. Like, what does that really mean? And we'll see again that we can give nice problems that really capture the essence of NL. So now let's try to look at what NL completeness is. And just to remind you, so you have L being NL being in P. So L is log space machines, and NL is non-deterministic log space machines. Now, you have observed in this course that there's this notion of completeness, which is very useful in understanding a canonical problem for a class. Now, the problem, the naive definition of NL completeness what would the naive definition of NL completeness be? We'll see where that fails. So we'll say, okay, so we'll say L is NL complete. L is NL complete if L is in NL and for all L prime in NL, L prime reduces to L. What is the problem with this definition?
My immediate guess would be that it would have to do with the polynomial reduction.
Okay, and what is the problem with the polynomial reduction?
Probably makes it so that if you actually give a polynomial reduction, then
you're almost there. Yes.
Yeah. I'm not exactly sure how to formalize it, but I think that it would be too large. That you need a smaller reduction.
Yes, that is in some sense. Formally speaking, the problem with this definition is that with this definition, every non-trivial language in NL is NL complete. Everything becomes NL complete. Why? Because NL is in P. So in polynomial time, I can actually solve the problem. I'm going to write this down. This is, I guess, is important to understand reductions. Under this definition, by non-trivial I just mean it's neither the empty language or the full language. So every non-trivial L in NL is NL complete. Let me give you the reduction. So given L prime in NL, so I'm giving you the reduction here. Since NL is actually in P, remember NL is in P, that's because you can just build a configuration graph. And the configuration graph has polynomial size. So you build the configuration graph and then you go ahead and traverse it. You figure out whether your instance is in the language. For any x, we can decide if x is an L prime in polynomial time. And so if x is an L prime, output some w in L, and if x is not an L prime, output some w prime that is not null. And that's why you need L to be non-trivial, right? This is where I'm using that L is neither empty nor all strings. And you need this for all lengths, right? But let's say it's it's neither empty for all lengths, or for all polynomially separated lengths. So this is okay. This is just a technical condition, but hopefully you understand the logic. It doesn't make sense to define efficient reductions with polynomial time if you're looking within polynomial time. If you're trying to understand the structure inside polynomial time, then efficient reductions defined as polynomial time reductions don't make sense, because everything can go to everything in polynomial time. You can just solve any problem in polynomial time.
So obviously I don't think we have anything called P-complete, but
well, we do
oh,
actually.
We do. Okay.
We do.
Well, in that case, at least, if we do, then I presume that the definition for that as well does not use polynomial reduction.
Exactly.
Uses a different.
Exactly. So we need a more refined version of a reduction than a polynomial time reduction. And using that, you can then define P-completeness. And so what is that reduction? So does this does this logic make sense? So please ask me questions if this doesn't make sense. So we need a more efficient notion of reduction, and this is called the log space reduction. So we need to have something called a log space reduction. What this means is, in effect, the reduction can be computed in logarithmic space. But this is a little tricky because you need polynomial time just to write down the output. Like a log space machine cannot write down a large, we'll see how you can have a log space reduction write down a large output. So I'm just going to introduce some definitions here. So I'll say f is a function. So it's just some function from string. So think of this as your reduction function is implicitly log space computable if for all x any bit of f of x can be computed in essentially O of log of x space. So it says a function is implicitly log space computable if you can compute any bit with logarithmic space. So logarithmic space is really small. Essentially all you can store are indices of the input. Formally, so let me just write down a formal definition. Also, you need that the function, the length of f of x is at most polynomial. So I'll just say formally just to be really careful, there exists a C such that f of x is at most x to the C, and for all x the language yes, xi, where fxi is 1. So this is the ith bit. Right. L, this language is in log space. And also, what we say is that you should also be able to sort of compute the length of the output in log space. So this is just saying that L prime, which is just going to be xi, so that I is less than f of x, is in log space. This is just saying that you can also compute the length in log space. Right? So in log space you can decide is this more than the length or not. So in effect a log space machine can give you each individual bit of the output. And that's what it means for f to be implicitly log space computable. And then we'll just define, we'll say, so for languages B and C. So I'm going to use I'm not going to use L here because L often may refer to log space or the complexity class. So for languages, we say B has a log space reduction to C. So instead of polynomial time reduction, you can say a log space reduction if the reduction f is implicitly log space computable. So this is the lens that we will use to investigate things within P, which is now we can talk about log space reductions, which are even more efficient than polynomial time reductions. And you can see that if you have a log space reduction, then you have a polynomial time reduction, simply because a log space machine can be simulated in polynomial time. And to understand what is going on within P with respect to L and NL, we are going to use log space reductions. And we're going to use this notion of log space reductions and now we can start defining completeness as before. So we can define what does it mean to be NL complete. Just like we define NP complete, we can do NL complete. We can actually define even P completeness. What does it mean to be complete for P? And there is actually a natural problem that is going to be P complete, and we'll come to that maybe later on in the course. And so for the next few lectures, we'll be looking at NL and understanding what NL completeness is.